Welcome to Winchester Cafe Sci Online, and a special welcome to those joining us for the first time. A recording of this talk will be posted on our YouTube channel, where you'll find recordings of all our online talks. I'll put details of that in the chat. You can also find the links on our website, wincafesci.org.uk. If you enjoyed tonight's talk and you're not on our mailing list, you can sign up for it there to be notified about future talks. 2 years have passed since our last live event, and I'm pleased to announce that we're planning for our next event on the 4th of April to be live at our usual venue in Winchester, while still intending to stream for those who are not yet ready for public gatherings. Obviously depends on events not overtaking us. We're also working on our programme of talks further into 2022. After tonight's talk, we'll go straight into the Q&A, so please put your questions into the chat and I will either read them out or invite you to. That includes our viewers on YouTube as well, who are also able to submit questions. Tonight's speaker is Professor in Materials Chemistry at the University of Birmingham and co-director of the Birmingham Centre for Energy Storage. He has more than 30 years research experience in the area of solid-state materials chemistry, ranging from battery materials to solid oxide fuel cells. In these areas, he's published more than 250 papers in scientific journals and has written more than 20 review articles. His present research is focusing mainly on the development of ionic and mixed conductors for energy storage and conversion applications, for example, lithium, sodium-ion batteries and solid oxide fuel cells, as well as strategies for recycling such materials. He's also active in promoting research into new energy technologies in schools and to general non-scientific audiences. We're very pleased to have this subject covered by Professor Peter Slater, so please give him a big welcome. Thank you.
Thank you. And thank you for the invitation. So yes, I'm from the University of Birmingham, and the backdrop I have is from the Birmingham campus with the chemistry department to the side of me and the old Joe's clock in the background. And so I'm going to give a talk about energy storage technologies, specifically battery technologies. And so why do we need them? Well, obviously we're all aware about the growing concerns regarding increasing CO2 emissions and diminishing fuel cell reserves. And this is driving research into cleaner energy technologies. So in some of the optimum sort of clean energy technologies are sort of the renewable energy technologies such as wind and solar. So these work obviously very well when it's windy or when it's sunny, but the key challenge for these technologies is their intermittency. So we need, particularly if we're going to expand our renewable energy technologies, we're going to need some way of storing this energy at times when there's an excess, so that we can use it at times when there's a deficiency. And so there's a number of possibilities for that one. Some examples could be, like I'm going to talk about, large-scale battery storage, or some other areas that I'm interested in terms of electrolysis. We could use the spare electricity to electrolyze water into hydrogen and oxygen, and then use that hydrogen at a later date to regenerate electricity. So other government strategy is to move to electric vehicles, so move away from petrol and diesel. And this is because of the significant amount of emissions that come from the transportation sector. And again, if you're thinking about approaches for cleaner these electric vehicle transport, then you're talking about things like electric vehicles powered by lithium-ion batteries, or you're talking about fuel cell vehicles, where again you're using hydrogen combining with oxygen to generate your electricity to drive your vehicle. So anyways, the talk today though is going to focus on the lithium-ion batteries, and I'll briefly mention also sodium-ion. So lithium-ion batteries are highly effective devices for the storage of electrical energy. They're high energy, they store a lot of energy for their size. The key application is they're rechargeable, and they're current batteries. You can, the rechargeability is the lifetime of the battery, the number of cycles you can do is improving day by day. And this gives us a wide range of applications. So the lithium-ion batteries technology took off to power portable electronic devices, and we wouldn't be where we are today with mobile phones, laptops, if we hadn't got the lithium-ion battery that helped to essentially make these devices much smaller. They're also used in power tools, but the big push currently is to extend them to electric vehicles. So examples, things like the Nissan Leafs, the various Tesla cars, and every other manufacturer is also developing electric vehicles. And there's also interest, as I'll show you, in using lithium-ion batteries for off-grid storage. And so although lithium-ion batteries is attracting more and more attention recently, they're not actually a new technology. They were first worked on by Stanley Whittingham in the 70s, when there was the oil crisis in the 70s, and they were looking at alternative energy storage technologies. And then Goodenough and Yoshino in the 80s improved on the battery, and ultimately led to what we currently see as the working lithium-ion battery. So as I say, not the new technology, but it took quite a long time before the three, Goodenough, Whittingham and Yoshino, were awarded the Nobel Prize for their work on lithium-ion batteries. Okay, so what are these batteries? Well, essentially they consist of two electrodes, a lithium transition metal oxide electrode, the original one being this from Goodenough, this lithium cobalt oxide, another electrode which is typically graphite. These are attached to a current collector to take out the current, and then they're separated by an electrolyte. And the key things of these devices, what we're doing is we're taking lithium out of our transition metal oxide material, and we're inserting it into our graphite. So that's what happens on charging. We're moving from that transition metal oxide electrode into the graphite electrode. And then when we use the battery, basically the lithiums will go back. And so that's the beauty of the device. We're just essentially we're operating them by shuttling lithiums from one side to the other. And I've put just here sort of the comment, although essentially the operation of these things essentially reverses depending on whether if you're doing charge or discharge. Battery researchers essentially refer to this transition metal oxide electrode as the cathode material and the graphite as the anode material. And what I should say is that this electrolyte is basically typically a lithium salt that's dissolved in an organic electrolyte, a hydrocarbon electrolyte. So one of the things we go out to schools and things and try and explain how batteries work. And one of the ideas from one of my group is that we can actually use Jenga to actually explain the operation of these lithium-ion batteries. So I'm going to show you some examples. So if we think of our situation, we've got our cobalt oxide, lithium transition metal oxide, and then we've got, let me just move that away, and we've got our graphite. So when we're charging, we're putting the lithiums from the one side into the graphite layer, and then when we're just discharging, they're going back. And the beauty of the way they work, these materials work, they can work quite well like that because they're all nice layered structures that will allow the lithium to be removed and to be reinserted. And you can also try and explain to a certain extent why the challenges with charging of these materials. So like Jenga, if you're taking a block out of Jenga, if you tend to do it quite carefully to make sure you're not knocking everything about. And it's similar in some respects to when you're charging your battery. You'd want to be able to remove this lithium quite carefully, quite slowly. That allows the structure to relax as the lithium's removing. If you try and remove it too fast, then you can potentially lead to damage of your material. And then again, you can start to use it to degradation. So even if you're putting in relatively slowly over time, things will get knocked about, and the structure hasn't got a chance to fully relax. So you haven't got this perfect structure that you had to start with. So you can start to get some degradation due to this. So that shows you essentially how they operate. So what are the characteristics we're looking for when we're trying to work on a new material to try and put it in a battery? Well, we want a high capacity, and what we mean by that, we want to be able to remove a lot of lithium and then put it back into the material. And the more lithium we can remove, the more energy essentially we can store. Obviously, there's concerns about a lot of the comments in terms of electric vehicles relates to the range of them and then them recharging of them. And so one of the things we want to do is actually trying to get faster charging, discharging. So we want to get structures that enable us to rapidly remove the lithium and reinsert it. And we also want, the final thing, we want to sort of improve safety. These devices are inherently very safe, but as with any technology, there's always things that can go wrong. And so the challenge is to make sure, limit the possibility of that happening. So again, in terms of sort of challenges, a lot of the work's going on. There's interest in large-scale energy storage applications, improving the energy density and charge rate. Something I'm going to talk about that's going to be probably a particularly challenge in the future is the sourcing of the metals and recycling. And if we want to grow the UK battery industry, we need to start educating people and building expertise in battery technologies. So there's a lot of interest worldwide in trying to increase the energy storage, reduce the cost of the battery, and increase this ability to charge rapidly. So if we think about the energy that the cell can store, the key thing that would dictate the energy is how much lithium we can reversibly remove and insert. So if we can remove more lithium, then essentially we're getting more electrons out of our material, and so consequently we're getting more energy. The other thing that's important is the weight of your material, because again that relates to the energy. And there's, if you look at sort of literature, people will talk about gravimetric energy and volumetric energy. And so if I start with gravimetric energy density, this is essentially how much energy you have divided by the weight of the material. And if we take two battery materials, so this was the original lithium cobalt oxide. This is a newer material, lithium iron phosphate. Tesla in particular are interested in this. It's a much cheaper material because it's got iron rather than cobalt. However, it's heavier. If you work out the relative molecular mass of this compared to this one's got a higher relative molecular mass. Each of them have one at lithium. And so the energy density of this one is higher because it's a lighter material. We can, in theory, remove the same amount of lithium, but this lithium cobalt oxide is lighter, and so its energy density is higher. Another one that's possibly in some respects better to judge for, particularly for vehicle applications and also smartphones, is volumetric energy density, because people are a little, particularly think of your phone, you're not so much worried about the weight of your battery, you're worried about the size of the battery, because you want you want a relatively small battery that packs a lot of energy to fit in your phone, so you're not carrying around a brick like in the old days when there was the mobile phones, when they were really heavy, basically partly because of the battery technology. And similarly in cars, if the smaller your battery, the more of them that you can pack into the car, and so the greater driving range you'll get for the car. So some materials that people report in the literature have very good gravimetric energy density, but because they don't pack very well, they have quite poor volumetric energy density. And so when we're thinking about making a battery, we need, say, the maximum lithium we can remove and reinsert. We ideally want a lightweight material, but we also want a material that can pack quite easily. And then the final thing that dictates the energy of the cell is essentially the relative stability of the lithium in the two electrodes. So we're shuttling lithium from one electrode to the other. And when we charge the battery, we're essentially driving it uphill. We're going to an unfavorable situation. And then when we're using the battery, it's going back downhill to a more favorable situation. And that sort of difference in energy between those two electrodes, the lithium in those two electrodes, will dictate the cell voltage and consequently the overall energy of your battery. So if we're looking at how much one of these batteries cost, we need to think about the cost of the elements, the starting materials, and the cost of production. Now, the cost of production has dramatically decreased over the last 20 years. So if you look at lithium-ion batteries, their cost has come down significantly. And a lot of this is related to the cost of production, moving from a small-scale production to these gigafactories, where you're making it, mass producing these batteries. So the key thing that's actually driving cost at the moment is probably the starting cost of the materials. So if we look at the sort of materials that are in, obviously lithium, we've got cobalt. Because cobalt's expensive, there's we're essentially replacing a lot of the cobalt with nickel and manganese. And then we've got our graphites as the other electrode. And so in particular, the cost of things like cobalt, nickel, and getting a bit more costly lithium is driving the overall cost of the cell. So gains that we're making by improving production are being partially taken out by increasing cost of the elements. And another issue is there's where a lot of these resources are located. So a lot of the resources in batteries, particularly cobalt, are located in certain areas. So cobalt, a lot of it comes from the Democratic Republic of Congo. Even lithium, there's a lot from Chile, also Australia. And so one of the challenges is in terms of sourcing some of these materials. So a lot of the car manufacturers are signing essentially long-term deals with mining companies to secure their access to these elements. And so there's also a lot of interest in finding new resources. So in the UK, in Cornwall, there's a lot of interest in mining lithium, either from geothermal waters, so Cornish Lithium doing a lot on mining from geothermal waters, or standard rock mining, sort of British Lithium and to a certain extent Cornish Lithium. If you wanted to know more, there's this article about cobalt from the Faraday Institution. And if you're interested in spirillers, there's this book which is about cobalt and batteries and the challenge in sourcing the cobalt, that was written by the late David Middleton. Okay, so I mentioned the key things that we need to optimize our energy. So what are people working on? So the original material that Goodenough looked at was lithium cobalt oxide. So it's got this layered structure that I mentioned earlier with lithium in between the layers. And the issue is cobalt's high cost. There's also concerns regarding the sourcing of it from the Democratic Republic of Congo. And so there's a lot of interest in replacing the cobalt with other elements. And so at the moment, most of your battery in your phone and batteries in cars, rather than being this lithium cobalt oxide, will be this so-called NMC material. So it stands for nickel, manganese, cobalt. And so what it is we've replaced a lot of this cobalt by nickel and manganese. So in some of the cars, for example, current cars, you're probably talking about between 20% to 10% of these metal sites are cobalt. So we've gone from 100% cobalt to 20 to 10%. And there's a lot of interest in trying to eliminate cobalt altogether. Now, because of the cost and sourcing issues of cobalt, and also growing cost of nickel, this material, this lithium iron phosphate material, this is no longer layered. This is sort of has iron octahedra separated by phosphate groups, and then these gray groups are the gray spheres are the lithiums. And this is a much cheaper cathode because it's got cheaper materials, iron, but as I said before, it's heavier, and so it's got lower energy storage. So companies like Tesla are looking at these for models where you're less concerned about range, but what you want is a cheaper battery. And then the newer research, the sort of things that we're working on as part of this, the CapMap project, is these so-called lithium-rich disordered rock salt materials. And the key thing of these, instead of one lithium, we've got more than one. So we're increasing the amount of lithium in our material. Overall weight is fairly similar. And so if we can increase that number of lithium and consequently remove more, our energy goes up. And so these in principle give very high energy density, but at the moment there's issues to be solved. Their reversibility isn't as good at the moment as these materials. So they give very good, much higher energy density to start with, but it rapidly fades. So it's trying to understand why it's fading, what's the degradation routes, and trying to develop ways of overcoming these. So I mentioned, obviously, there's one of the concerns about electric vehicles is the so-called range anxiety. Sort of at the moment, as battery technology is improving, and so the range of these cars is dramatically increasing. But there's still concerns regarding the time it takes to charge. And so there's a lot of interest in improving the rate capability of these batteries, make their ability to rapid charge while still delivering the same amount of energy. So in terms of if you want really rapid charge, so if you're looking at charging, say, in 6 minutes or less, which you might need particularly for a rail and motorsports, then basically they typically use, these sorts of batteries typically use similar cathode materials, so these layered lithium transition metal oxide, but rather than graphite, they'll use a titanium and or niobium oxide based material. And one of the biggest challenges regarding rapid charge is actually the graphite. What will happen with graphite if you rapidly charge? The lithium will go initially between the layers, but if you try and charge too fast, you start to plate lithium. So you put lithium metal on your anode, and that will cause you potentially safety issues. So the limiting factor of a conventional battery in terms of fast charge is mainly that graphite. And so that's why there's this interest in alternative electrodes. So I mentioned the developments for the cathode. So in terms of the anodes, as I say, the conventional battery and all the batteries you'll have currently in your phone and also in cars will be graphite, or it will be graphite with a bit of silicon added. So silicon gives you a higher energy storage capability, but you can't use silicon just on its own because it expands too much and would cause, it wouldn't be very reversible, but you can improve the performance of a graphite electrode by adding some silicon extra. So that's the conventional. Then if you want to go to rapid charge, then you could use this lithium titanate material, which has the spinel structure. And this gives you safe operation at very rapid charge. However, its energy storage, the amount of lithium you can insert into this material is comparatively low for its weight. So it's relatively low, lower energy storage than the graphite. And so the ones that really attracted attention are these niobium containing. So I've given one here, this titanium niobium oxide, but there's a whole host of these materials that have interesting sort of so-called shear structures. So you can hopefully you can see some corner linking of octahedra, and then you have these edge sharing of octahedra. These are so-called crystallographic shears that stabilize the structures. And these are highly stable materials. They're excellent for insertion and removal of lithium, and you can do this at very high rates. So you can start to think about charging your battery in 6 minutes or less with one of these materials. And as I say, there's a whole host. Some give you higher energy density and say might give you 10 minutes charging. Others might give you slightly lower, but may give you 3 minutes charging. So you can get, again, you can choose a material that suits your application. Do you want really high energy, relatively rapid charge, or do you really want that rapid charge but can cope with a little bit less energy? And the other interest and there's a huge amount of interest in the news about this, and these are seen as the sort of next step is the solid state batteries. So I mentioned at the start, your conventional battery has a liquid electrolyte. It's a lithium salt in a hydrocarbon solvent. And so one of the issues with those is you can't use lithium metal as your anode, otherwise it would give safety implications, and that's why you use graphite or one of these other electrodes. If we could replace our liquid electrolyte by a solid, and a non-flammable solid at that, then we introduce inherent extra stability in the material, and you can start to think about using lithium metal as your anode. And that gives you much higher energy storage, because ultimately, and I said, the key thing is the amount of lithium over the weight. Well, if you've only got lithium metal, it's the most energy density you could ever get for an anode. So these have huge potential, and there's a number of companies in the UK. There's Ilika, who have commercial small scale solid state batteries at the moment, and are developing larger scale batteries for EVs. There's companies like Solid Power, QuantumScape in the US that have attracted a huge amount of interest, and so there's great potential for these solid state batteries. But again, there's still challenges to overcome. One of them is in this case manufacturing. We're very well sorted to manufacture the conventional batteries, but it's going to be different to manufacture these solid state batteries. So once the materials are optimized for the performance, the next step is also trying to optimize the manufacturing process so that you can produce a cheap solid state battery. So I just now talk briefly about some recycling. So one of the things we need to think about as we move to changing to electric vehicles is we need to think about how to recycle these batteries. And we've written this article in the journal Nature, on a review article. That's the link there. It's open access, so completely free to read. Anybody can read it. So that has a lot more detail. But as I say, what we need to do, we're going to have at some point in the future, if we move to all EVs, we're going to start to get a constant stream of cars, batteries that come into their end of usable life, and we need to consider what to do with them. There's two things we could do with them. We could use them in a less demanding so-called second life application, and I'll talk about that briefly later, or we could recycle it. And there's a lot of benefits in recycling it, because I mentioned some of the challenges with sourcing elements. Well, when you have a used battery, you've got now a source of valuable metals that you could then recover and then reuse in a future car. So this circular economy of recycling these batteries is going to be crucial to actually preserving the supply of these important elements. But there's a lot of challenges. We've got to remove the battery pack, and I'll show you what one looks like, I think, on the next slide. We've got to ideally separate out the individual cells. So the battery pack has a large number of cells in it. Ideally, we might want to open those cells, because that makes it a lot easier to recover the materials and then remanufacture them. So this is essentially the insides of a Nissan Leaf Gen 1 vehicle that we dismantled. Well, some colleagues of mine on the Really project at Newcastle dismantled. And if you wanted to see the dismantling of this battery pack, on the Relib website, there's a video that will goes through the whole procedure of basically making the battery pack safe and dismantling it. So you can see there's in these cans are all your lithium-ion battery cells. There's various other electronics, and essentially it's a very high voltage overall. So there's a lot involved in its dismantling. You've got to think about the voltage safety, and then you've got to start taking out these the individual groupings of cells and then dismantling those. So how do we go about recycling these materials? Well, the generally dominant tech method at the moment, and this is related to the fact that it's quite challenging to dismantle. So Umicore in Belgium essentially use pyrometallurgy. So what that means is they will incinerate the batteries, and then through their processes they will then recover the valuable metals, in particular cobalt, nickel, and some of the others, and then they can then supply them for use to make new batteries. But as I say, that's not ideal, because you are burning off a lot of the materials, you are creating emissions. Admittedly, their process cleans the emissions, but ultimately there is some benefits to other processes. So there's a hydrometallurgy approach. To a certain extent, their procedure also introduces a hydrometallurgy step. So in hydrometallurgy, what we would typically use is we separate out the individual cells, and we would leach the battery electrode materials off the current collectors using acids, and then we will sequentially try to separate those metals. So that ideally will recover a lot more, but again, it's still an involved process. So ultimately, my colleague at Birmingham, who runs the RELI project, talks, this is sort of recycling 1.0, this is sort of recycling 2.0. The ultimate aim is to get to recycling 3.0, and that's direct recycling. And that's basically what we do in that. I mentioned that there can be some degradation of the material during time, but ultimately most of that material is still good. So is there any way of us doing a very simple step to just take that material and repair that degradation without dissolving it up or anything like that? And then that's a much cleaner process. So we're looking at what's the degradation in these materials, and can we repair that degradation simply? And another important thing that we're trying to push as part of this project is the need to design these battery packs for recycling. As I mentioned, it's quite an involved process to separate them. And so we're looking at things like trying to highlight the challenges, what things cause issues with recycling, but also trying to develop things like robotics, robotic dismantling of these cells. So in Birmingham, on the Tyseley Energy Park, we've set up a prototype robotic dismantling centre. That's run by some colleagues of mine in metallurgy and materials. So what does one of these cells look like? So in those little canisters, there's a number of these individual cells, the individual cells. So that's what one of these look like. If you disassemble them, you can see this black material, essentially your cathode material. We could do a number of things. We could shred it and sieve different components, or we could just directly leach this to create our solutions. And then we can regenerate our material and then put it back into a battery. And one of the things we can start to do is we can take a material from an old cell that may have higher cobalt content, and we can remanufacture it into a new material, new cell that has lower cobalt content, that's more used. So take old lithium-ion battery materials and use the components to regenerate a new lithium-ion battery material. Okay, so I mentioned EVs, but what about other applications? So large-scale grid storage. So there's a lot of interest in using these lithium-ion batteries for homes or buildings. So if you take Amsterdam Arena, this is currently powered by a number of renewables, but with energy storage from essentially Nissan Leaf battery packs. So this is an example of taking car batteries and using them to power a building. And this is viewed as a so-called potential second life use for lithium-ion batteries, because in electric vehicles, the batteries in electric vehicles are very high spec. They need to be high spec. They need to be able to survive a very demanding environment, their use in a car. And so what's normally classed as an end-of-life battery is one that gets down to 80% of its initial energy. So it's still pretty good, still can store 80% of what it had to start with. And so it's got a number of potential for other applications, such as buildings, where the environment's not so demanding. And so there is interest in using the batteries for second life before that you ultimately then want to recycle them, because at some point, again, even in the second life, they'll be no good even for the second life application. And so you will have to recycle them at the end, but you could still get potentially 10 years or maybe even more from these used batteries. So there's a lot of interest in lithium ion for stationary power application, these buildings, but the challenge is the cost of lithium is increasing. At the moment, you still need a bit of cobalt in these cells to get the best materials, and that cost of that increasing. And so there's a lot of interest in cheaper. And so the sodium ion are attracting attention. So sodium has similar chemistry to lithium. And so will work quite well in a battery operating quite similarly. And so in the UK, the company Faridian have done a lot of work on these sodium ion batteries. And it's not just the fact changing from lithium to sodium, it's the fact that sodium ion electrode materials work very well without cobalt. So we don't need cobalt. The challenge for the sodium ion tends to be they don't last as long as a lithium ion battery at the moment. So it's trying to increase the lifetime of the cell, but they're a lot cheaper. Okay, so I'll just finish on by, we've got a lot of resources that highlight. So if anybody's in schools or we mentioned our Jenga with my student Lizzie has produced a range of guides and worksheets for school children based on GCSE, A-level, Scottish, National and Scottish Higher curricula. So those are available on my group's website, which is just prslate@chem.com. We did for the RSC, we did a human battery to show how lithium-ion batteries operate, and it also shows some advanced characteristics of something called the solid SEI layer that forms. So that's can be found via just look at Lithium Shuffle project. And one of the things we're trying to get across is not just the materials like in the Jenga, but how you go about manufacturing these batteries. And one of the things, in some respects, you can relate manufacturing a battery to making a cake. When you make a battery, you've got your individual materials. Similarly, if you bake a cake, you've got your individual materials, but you've got to actually put them together correctly. You've got to mix the materials well to actually get your perfect battery. In the same way, you've got to, if you're hopeless at cooking like me, you'll bake a bad cake. So you've got to know the procedure. You've got to know, make sure the mixing is correct and all the components are correct. So you can think of mixing of the different components of the battery. You can think of the different parts of the battery in relation to a cake. So you've got one, your cathode material with all the chocolate chips here to represent the lithium ions. You've got your filling, which is the electrolyte. You've got your other layer, which is your anode, and you've got some syrup, which represents a bit also the electrolyte that needs to soak into both the electrodes to show those the fact that you can essentially correlate some of the things with making a battery to some of the challenges you have when making a cake. And also there's a few experiments for students to try icing electrode, custard electrodes, to show how when you're making electrode inks, you need to control things like the viscosity of those inks, and shows you how you can change things, for example, in your custard to control the thickness of the custard. And it's a similar thing when you're making electrode inks. And then the final thing, we've started to interview people working on batteries in academia, but also in industry, to highlight the battery jobs to school children. So companies like Ilika, who've been working on solid state batteries, Cornish Lithium, who've mining lithium, JCB looking at electrification of those. So if you go to the group YouTube page, Birmingham Battery Bunch, you'll find some of these. So the Ilika ones, there's a couple of Ilika ones already up, the Cornish Lithium ones already up. We're still editing the JCB one. And I'd just like to thank some of the, particularly the Faraday Institution for funding a lot of this work, and also the EPSRC for funding, and members of my group for their work and on some of the science, but also on some of the outreach. And this is my Twitter, and this is my group website where you can access some of these resources. And thank you for your attention, and I welcome any questions.
Thank you very much, Peter. That's a fascinating tour of a subject I feel I really should have known rather better. I was particularly disappointed in myself for not having realized that the actual weight of cobalt in a battery is so much higher than lithium. I just sort of assumed, oh, it's probably some sort of catalyst there in a small proportion. I hadn't realized it was stoichiometrically equal. So that was
yeah, I mean, there's interest in trying to eliminate the cobalt, the transition metal altogether. So you might see in the literature so-called lithium oxygen batteries, where you're forming lithium peroxide. And in that case, you do add a little bit, you might add a little bit of a transition metal oxide as a catalyst for that process. So unfortunately, they don't cycle very well at the moment.
Okay. Do you want to stop your screen share now? I'll just do a bit of sort of continuity. So please, let's get some more questions into the chat for after the break. There's a few there already. Well, sorry, we're not taking a break, but carry straight on. Got a few there, and we'd be welcome to have some more. Before that, a quick heads up on our next talk on Monday, the 4th of April. The talk will be Humans and Animals in Roman Winchester and Beyond, from Professor Mark Maltby at the University of Birmingham. And it will be back at Winchester Discovery Centre, or Winchester Arc, as it's now rebranded itself. It's under new management, and we're going to be trying to stream it at the same time as having a live event. We'll probably also restrict the number of places that are available, but I hope that will be popular with lots of people, and perhaps talk about that sort of later on. But in the meantime, please come through with your questions for Peter on that, on the subject of tonight's talk. Let's just put the spotlight in. So one of the questions we've had is, how thick are the layers in your Jenga battery? I assume that means that not the actual Jenga battery, but sort of the actual real life battery that you're modeling in Jenga.
You're talking about sort of anywhere in the region, I guess 50 to 200 microns. So there is a challenge to, ideally you want to go as thick as possible, because then again it's ultimately your electrodes that are dictating how much energy you can store. So the thicker you can have them, the better. The challenge is you've got to make sure that the electrolyte will wet all the way through those electrodes, and you can get the lithiums in and out into the electrolyte, and so that generally dictates the thickness. So one of the things we are working on in the next road project is ways of making thicker electrodes, basically.
Okay, I guess that's not so much an issue for handheld devices, but it's
No.
an opportunity for
it's an opportunity. It's one way of increasing the energy, essentially your volumetric energy density of and your gravimetric of your battery.
Yeah. So I had a question: are used car batteries available yet for use with household solar panels for storage fitted retrospectively? Somebody's saying they've just had solar panels, but the batteries to go with them are incredibly expensive, and the cheaper alternative would be a huge benefit.
Yeah, not that I'm aware of. I think the challenge is at the moment, because obviously electric vehicles, although the numbers that have been sold are growing, there's still comparatively few, and a lot of them are new, and these car batteries do last quite a long time, and they look for a lifetime of 8 years, but from the looks of it, they'll last longer than that. And so I think even in the Amsterdam arena, those were actually the ones that we used there, what might have even been new batteries rather than used ones, because again, there's not enough coming through. The sort of ones that come through are things that have been in accidents, for example, cars that might have been in accidents, which then you've got to recycle them. You're never going to, once the car's been in an accident, you're not going to use that battery in a second life, just on the off chance there may have been some damage done by the accident.
So you wouldn't give them a second life in a building either, because
no, you want to. I mean, the other thing you've got to think about with second life, and this is possibly one of the bigger challenges, is, and I think it relates to a question. Well, maybe I'll ask one of the questions, because I did see one and it sort of relates to this. Let's just see what it was. Oh yeah, so there was a question from, is degradation linear or does it accelerate once it sets in? Well, the degradation would depend on the operating conditions, but generally it will start off linear. However, it looks like the at some point in the life of the battery, there's a so-called knee point where it completely fails the battery. And one of the things is trying to understand that and trying to model that, because, and this relates to the second life application, because if you've taken a battery out of a car, you want to know, you want to be able to test it and say, we believe we can guarantee there's going to be this number of years of life in the battery for your application. And so it's one of the things we're trying to do in the ReLib project is understand when these batteries take through this knee point where they completely drop off performance, what is causing that? So can we predict it?
Interesting. I've seen a few discussions in some online forums around solar battery storage, and people suggesting buying an early, if you've got a bit of space on your drive, buying an early Nissan Leaf and just using that as your battery.
Yeah.
You've got about 24 kilowatt hours in. It's actually quite a cost-effective way of doing it.
Well, I mean, as I say, that was one of the challenge we had with the recycling project. It was trying to get an end of life batteries to look at. So we literally did buy that Nissan Leaf to use Nissan Leaf to take apart and investigate. So investigate essentially taking these batteries to their end of life, full end of life, and monitoring what's happening to them.
Yeah, indeed. I've got to, so there was also a question earlier on. Robin was asking, could you talk a bit about the safety of lithium-based batteries? There have been lots of stories in the news about phone batteries catching fire, large Tesla batteries catching fire, etc. Why does this happen, and what can be done about it? Okay, so I mean, partly talking about the plating of electrodes as one.
So possibly the phone batteries, I think the Samsung ones, that was actually, I believe it was a design fault in the battery, and this goes back to this again, what I'm talking about, volumetric energy density. People want small batteries, and so I think what they were looking at is trying to get as thin a battery as possible. And I think in some of the batteries, what happened was the current collectors, basically, because it was so thin, that batteries, and there was a bit of deformation, they could partially touch and short circuit, and that was what caused some of them to go. So that one was more a design fault in the batteries. Car batteries, particularly, are generally manufactured to much higher specs, so they should be very good. I think the challenge with particularly maybe the early Teslas, I'm not so sure about the later ones, but they used a large number of so-called 18650 cells, which are tubular cells. And so they're not like pouch cells, which is the ones that I showed on my slides, which were taken from the Nissan Leaf. So they use these tubular ones, and from what I gather, there's a known that those work very well, but there's a known failure rate of those. And so if you have thousands of them in a car, it might be a small known failure rate, but if you have thousands of them, then that probability increases. And so it may just be simply one issue with one cell. The other thing you can't, I mean, that's what I suspect is the case, but I'm not an expert by any means in terms of what's in these individual car components. But I think if you look at the likelihood of an EV fire versus the likelihood of a petrol fire, it's far less likely to have an EV fire than the petrol car fire.
Yeah, good point to come back to. So when you're talking about having these multiple tubular cell things, presumably these are arranged in series to get the voltage that you want. But if one of them fails, then that's the whole circuit.
No, I mean, they'll have various, there's in these cars, there's various battery management module. And so I'm sure there must be some way that they can bypass issues with
a remap or something.
Yeah. So as I say, it's not my area, but I'm sure as part, if one sort of mini component collection of cells failed, I'm sure that the battery management would be able to cope with that and bypass it. It would mean obviously your energy would go down, but I don't think it's not going to be a case that one battery and everything goes.
Okay. And you have to remind me if I repeat any question, because my brain's still off for the COVID. But Don was saying, is there any simple cost benefit measurement of the range of processes involved in resourcing, like mining, transporting, and including recycling and disposal of undesirable residues? You might want Don to explain that, because there were a lot of words in it.
Yeah.
Yeah, William never understands my questions. It just seemed to me, Peter, that you've got a series of processes, all of which you're paying some attention to, and you're searching for life and durability of the result. But generally, if you have a cycle of processes, it dries up unless you inject something into it, and that's normally money. And that's a question of affordability then. Do we see a convergence of the cost of these processes the series of processes that you're addressing against affordability? Or do we just wait until everybody is so conscious of the environment that they will use their life savings to buy a battery?
I think the biggest challenge in terms of reducing cost is the cost of the elements themselves, the mining of them. As I say, manufacturing costs is coming down. If we can go, for example, to thicker electrodes, that's going to drive down costs as well. There's interest in these alternatives, so lithium iron phosphate. So that's been very much viewed by a number of car manufacturers as a way of dramatically bringing down the cost, because you're using much more abundant elements. The recycling actually is an interesting one, because at the moment it's cost effective to do the recycling because of the cobalt and the nickel. The challenge is going to be, if with these lithium iron phosphates, there's going to probably have to be legislation for them, or some money in the cost of the battery for somebody to then recycle them, because you go into a cell where actually the metals aren't that valuable, apart from maybe the lithium and maybe the phosphorus.
The danger is you then dump them in the sea.
Yeah, well, this is why I think there's, well, certainly in the EU, they're starting to introduce battery legislation regarding these vehicle batteries, so that I think there's going to be a responsibility on the manufacturer to take them back and recycle them. And there's also going to be a requirement to have a growing percentage over the years of recycled elements in future batteries.
Yes, I must admit, I was looking at the analogy to nuclear fusion, you know, where we have this potentially great advantageous process in the future, which will produce more energy than we can ever use. But on the way, it's using more energy than we've got because you get less out than you put in. And your processes with batteries are in danger of meeting those sort of hurdles.
It's a different kind of scenario because fusion is primary generation and batteries are about managing the transmission of it and the storage.
Fair enough.
Yeah, I think we've probably answered Alison's question about whether batteries are currently recycled in the UK, and it's simply this, that there aren't enough of them coming round for recycling.
Yeah, I mean, there's some companies starting to look at them, and there's some reports of plans to do it. There's certainly plans afoot to introduce recycling facilities.
There's a question about how bad a crash do you need to write off a lithium car battery, but what you're saying is doesn't matter how bad, you take the precautionary principle and you write it off anyway.
Yeah, I mean, I couldn't answer that question accurately. I mean, I think if there's any indication that basically these batteries have quite a design to withstand the crash for safety. But I guess if there's any evidence that the outer casing has been dented or been hit or something like that, then there'll be some concern regarding.
Sure. You'd want to know that if you're leaving it in the car and if it had another accident, that was still going to be safe.
Yeah, but as I say, they're well designed, these things, and they're tested to see they will withstand serious hits, basically.
Yeah. Okay. Jeff's asking, what makes batteries in EVs more practical than using fuel cells to power vehicles?
I think the biggest challenge, probably with the fuel cells, is the infrastructure, both the infrastructure for the generation of the hydrogen to power them and the infrastructure for the distribution. And so I think that is the biggest challenge with for fuel cells. Otherwise, if that wasn't the challenge, I think fuel cell cars would be there'd be a lot more coming out onto the market. That you'd be seeing a lot more on the roads.
Hydrogen being a phenomenally difficult substance to contain, as well as its explosiveness. Yeah.
Well, I mean, the challenge is, I mean, there's these initiatives. I mean, Tisley Energy Park, they're using, I think, solar to electrolyze water to give you hydrogen, which is then going to power buses and even trains. So that's a central. So it sort of works there. You've got a central infrastructure.
Yeah.
And so you imagine sort of buses and trains where you could have a central depot that you're generating locally your hydrogen. Then you've got your ready access to the infrastructure, and then there's easy to get for the usage.
The other thing that relates to that is that those types of vehicles have much longer duty cycles as well. So the average domestic car is probably on about a 5% duty cycle, and the rest of the time potentially it can be charging, whereas trains and buses and freight vehicles need to be active a lot more of the time. Okay, one question was, what's the best way to preserve the lithium-ion battery life on an electric bike? So I suppose that means the sort of how you charge it and how often. I've heard some in varying stories about what's best for a lithium battery, not necessarily being the same as the sort of nickel-based batteries that we've had in the past.
Yeah, you probably want to be maybe operating it sort of between 20 and 80% charge. So not using it fully up and not fully charging.
Yeah.
And that's why I think some of these superchargers, they will take you up to, they will only supercharge up to about 80%.
Do the power management systems that these things have typically take account of that? And so when they say 100%, they only mean 80%, or because I mean, if I plug my phone in when I go to bed at night, it will take it up to 100%, because it kind of doesn't have a logical or natural means of stopping at that unless I happen to be looking.
Yeah. I mean, no, I suspect not, but I could be wrong. But it'll just, if you go between those, it will just make it last a bit longer. It won't. It's probably something you're not going to notice easily. It might be. It's probably one of these things that if you did one where you were keeping using it to the full and then emptying, and you keep the other in this range, you might find after a year you might start to notice, okay, the other one's working a bit better. So it'll give you a little bit more, but it's not going to vastly. They'll still work pretty well if you operate them.
Yeah. Okay.
Otherwise.
So with the sodium batteries, do the larger sodium ions move as easily between the electrodes as the lithium ions?
The biggest challenge for it's one of those unusual things. It can be yes or no. So in electrolytes, because you can get solid sodium ion electrolytes, actually some of the sodium ion electrolytes conduct as well as the lithium ion, because sometimes you can have the lithium being a little bit too small for some structures, and so rather than sitting in the middle of a site where it can move quite happily, it will move a bit off and get partially trapped, whereas sodium might be more sitting quite comfortably in the middle. The biggest challenge, and one of the things that I don't think still fully understood with sodium, is it won't intercalate into graphite. And this is a weird thing because lithium will, potassium will, which is bigger than sodium, so it's not a size effect, and so you can't use graphite with a sodium. And what you have to use is, you can use carbons, these so-called hard carbons, which are more not as uniform as graphite, and sodium appears to work with them, but they're not quite as good in comparison to graphite. So size, well, as I say, the issue with sodium is not so much the size, but this weird thing that it won't intercalate into graphite, which, as I say, is not a size effect, because potassium that's bigger will intercalate into graphite.
Do you think that's something that could potentially be overcome if somebody can work out why sodium's an oddity on that, or do you think that's probably going to be a hard stop?
I don't think you'll overcome it into graphite. I mean, what people are working on these hard carbons, so they'll make those better, or they'll use something like titanium oxide, like these high charge lithium anodes.
Mm. Jeff's asked, are large-scale grid batteries a realistic alternative to either nuclear power, presumably fission at that stage, or hydrocarbons with CCS? I suppose that's kind of it. It's pitting renewables against nuclear or some sort of vague attempt at being sustainable hydrocarbon to provide sort of continuity. What's your view on grid batteries?
Yeah, I mean, I think if you are going to go to increase the renewables, then it's essential. How, as I say, I guess it's relationed in terms of the nuclear. It's whether the government plans are renewable or nuclear. My guess is it's going to be a mixture of both.
I guess you're weighing that as well against other forms of energy storage, like gravity-based ones or gas compression and things like that as well. Yeah,
I mean, carbon capture and storage, personally, and this is, as I say, my personal opinion, I'm not convinced, because whatever we do, we need to make energy technology more efficient. And my issue with CCS is you're making it less efficient, because ultimately there's going to be some energy costs to trap, separate, store the CO2. So ultimately you'll be burning more gas, oil to produce the same amount of electricity. Okay, admittedly you won't be maybe liberating so much or potentially any CO2, but ultimately you're making your energy technology less efficient.
Yeah, I mean, my view is CCS and blue hydrogen are just attempts by the fossil fuel industry to try and stay in existence, and I don't think they're a very strong justification. Some years ago, must be about 7 or 8 years ago, I think, I saw a lecture from Claire Gray, she was talking about sulfur batteries.
Yeah.
I think you may have touched on that a little bit in the solid state thing. Is that something that's sort of fallen by the wayside, or is that a future generation?
No, I mean, there's interest in that. So that's, so I mentioned lithium oxygen, or that people call it lithium air, but as I say, it's lithium oxygen. So that's similar, where you've got no transition metal, and so you're relying on the lithium going to lift the sulfur redox, so you're going to lithium sulfide. So the challenges with that, with the liquid electrolytes, what happens is you start to get that can dissolve in the electrolyte, and you get crossover. So they fade faster than you'd hope. So they work, but they fade faster than you'd need. If you can get the solid state, then you can overcome that problem. That will be one way of overcoming that problem. But yeah, there's a lot of interest in lithium sulfur, and there's definitely the potential there for them. If you can, I think you can either solve this dissolution problem or get a full solid state working.
Interesting. Well, Professor Peter Slater, thank you very much for a fascinating talk. Certainly I've learned a lot about the things that I probably should have known about. Oh, Bob had one quick question. Go on, Bob. Sorry, before I wound that up.
Yeah, I just wondered if you'd had any dealings with bio batteries, because I know my own university, UEA, has been doing some research in this. And I believe the idea is you take a battery, it must be a case you fill it with something. So it's like a refillable battery, you put more stuff in it, and it's a bit like filling a car. Do you know anything about that?
I've not done so no, don't know too much about that. I mean, I had a little bit of experience from a colleague on microbial fuel cells, which again worked well. The challenge with, I think, with those, and maybe it's similar with the bio batteries, you only get a very small current, small voltage, and so they're not going to be for sort of high power, high energy applications like cars and stuff like that, but they may be for sort of low scale recovery of energy.
Okay.
I'm having difficulty adding to chat. Can I dictate a question to you?
Yes, of course.
I understand that you're doing the R&D now. Do you look more long term? For example, work out how much cobalt and nickel we will need to meet net zero targets?
Yeah, well, there's various people that were on the project on looking at life cycle analysis that were looking at that, and as I say, you say, it is a challenge, particularly for both cobalt and nickel, and that's why the sort of long term, what we're looking to try and do is get some of the cheaper and more abundant metals like manganese to work, or even iron.
Okay, well, I think that's probably a good point to wrap up now. Peter, thank you very much again, as I said, for a really interesting update on a subject that a lot of people have been asking about recently. So we're really pleased that you were able to come and talk to us today on that subject. A lot of really useful links in the slides as well. So I'll share some of those later on. And yeah, can I ask everyone, please give a big round of applause to Professor Peter Slater. Thank you.
Thanks for having me.
Thank you.
Thank you.
Okay, bye-bye now then.
Okay, bye.